couple of things. So today we're gonna together sit down and do the vorticity stream function approach, because I am a firm believer that you do not learn CFD unless you write a CFD code, one or more, and several more. Okay, so you have to keep writing a CFD code like once every 3 years. Just write a little code or do something, tinker around, and then if you're not going to be in the development of CFD, at least you have to do some data processing of CFD to kind of keep your head wrapped around it. So that's why I am going to be including a lot of hands-on programming CFD, even if we don't. I'd rather us cover very little, but go out mastering writing at least one simple CFD code or two, rather than covering a lot of math and theoretical stuff and have no skin in the game, okay? Because eventually you're going to develop an engineering understanding of CFD, even if you're just going to be a user. And the second thing, so I always listen to kind of podcasts. So I have a long commute. It can be really annoying, and so I end up listening to a lot of podcasts and audiobooks. And some of the podcasts I listen to are from kind of crazy people living on the fringes of society, like people who are doing homeschooling, for example, or people who are living underground or something, just to kind of listen to interesting things that are not conventional. And one podcast I listened to the other day, there was this guy. He has like 8 kids. He was a corporate manager at HP, and then he was laid off, and then he just decided to stay at home and homeschool his kids with his wife. His oldest is like 17 years old. His youngest is 3 years old. And he was challenging the traditional teaching approach that our schools have. So one size fits all. You go to school, that's the curriculum. We all have to study this, whether it makes sense for you as a person, as an individual or not. And that's the greatest contradiction of Western society from someone coming from a non-Western society where, in the culture I grew up in, the individual is important, but it's not about you. It's about the collective society as a whole. It's interesting that Western society is the opposite. So your kid has its own room, from when they're age 0, right? And it's the individual is very important. Yet our schooling system is so unindividual. You just go in and just sit in this class, etc. Anyway, but it's important to have structure. I'm not kind of criticizing that, but I can understand why you can challenge the traditional educational system. And one of the comments, one of the criticisms this person made is like what's happening in our schools with physics and chemistry classes, where you go to the chemistry chemistry lab to do an experiment, and you go to the lab and you have a set of instructions that you have to follow. I mean, what the hell is that? That's not an experiment. An experiment is when you go there and you're like, okay, I'm going to mix these two things together and see what happens, given some information about these two things. So what's happened to actually messing things up and learning from failures and mistakes and errors? That is more important than figuring out the vapor pressure of a system. Who cares? Okay, go measure the vapor pressure. I don't care. What am I going to do with the vapor pressure? Let me first make some vapor, and that's going to be fun, and then understand why I need to measure the vapor pressure, for example, or a reaction rate. Let me mix things together and have them burn and light them up, and burn things up in the lab. So, so anyway, the point is that podcast really inspired me, and I decided to. So I usually prepare my code before coming to class, just. And I make my mistakes in the comfort of my office. And trust me, I will always make a mistake. No matter how much expertise you have in writing code and CFD, if you think you know CFD, you don't know CFD. Feynman used to say that about quantum mechanics. Okay? If you think you understand quantum mechanics, you don't understand quantum mechanics. If you think you know CFD, you don't know CFD. Because every time you sit down and write a code, you're going to make a mistake. You're going to make hundreds of mistakes. So instead of me sitting in my office making the mistakes in the comfort of my office and then coming and showing off to you that, well, look at me, I know how to do this, I decided not to do that anymore. So I'm going to sit here with you, and together we're going to make mistakes, But the only difference is that I've seen this mistake before, very likely. And then I hope that the way I'm going to analyze and fix that mistake is going to help you figure out your mistakes in the future. What do you think of that? Great idea? OK. All right. So last time, we left off at the vorticity stream function boundary conditions. OK, CFD, spring lectures, vorticity stream function. So just to remind you of the boundary conditions that we settled on, we discussed all of that fun stuff. And we looked at the driven cavity. And we had stationary walls everywhere, and the top wall was moving at a fixed velocity. And we had the following relations. So we have a vorticity transport equation. It tells us how vorticity, called omega z over here, because it's in the z direction. That's a 2D plane, xy. Omega z, that's the only vorticity component that's non-zero. So that transports vorticity. It's an advection diffusion equation. These are the advection terms, and this is the diffusion term. Think of these guys. They're actually the velocities, OK? They're the velocity field. So these terms are advecting omega in space, OK? And the other relation we had was between the stream function and the vorticity. The only thing missing at that point were the boundary conditions. And so we went on and derived the boundary conditions. On the vertical walls, we first we looked at the value of psi across the entire boundary. So we looked at the normal velocity components at the walls. So on the left and right walls, u was equal to 0, which means d psi by dy along the wall, okay? Along the wall is 0, which means psi is constant along the wall, okay? So remember, this is along the wall. And then on the top and bottom walls, the v velocity component, the y velocity component was 0. So that gives us d psi by dx equal to 0, which means along the wall, psi is constant. And since these boundaries are connected, they are going to be the same constant. So in other words, really, the boundary is a streamline, OK? And that's going to be kind of our reference streamline, OK? Then we needed boundary conditions for the vorticity. So first, we listed the tangential velocity components rather than the normal ones, and those gave us deep psi that the normal derivative of psi at each point on the wall is 0. So, and we cannot infer that psi is constant here because that's only one point. This is deep psi in dx, okay? So the change in x is 0 only at that point, okay? Okay, and then we wanted to infer boundary conditions for the vorticity. So you go through the left and right boundaries. You eliminate the constant portions of, or the zero, so the constant psi, which leads to 0, second derivative for the d psi dx squared, d2 psi dy squared, and you're left with the following for the vorticity on the left, right boundaries, top boundary, and bottom boundary, okay? So, but that's still not enough because we need to get a concrete value for omega z that we want to place at all of these boundaries. Okay, and for that, we looked at a Taylor series of psi in the interior, okay, around psi at the wall. And the reasoning behind that is that that's going to give us a d psi by dx or dy, which is going to be equal to the tangential wall velocity, and d psi by dn, or d psi dx, d2 psi dx, d2 psi dy squared. That's going to give us the omega, and then we invert this relation to get omega at the wall, okay? And we finished. This is where we left off. Then we discussed what's going to happen at each one of those walls, okay? So I want you to open up your Jupyter notebooks, okay? I'm going to create a, let me see, where we started writing something the other day. Let's just start a new one. Python default. Okay. Okay. So I'm just going to import. That's the only thing I'm going to copy. I'm just going to import the boilerplate stuff. Okay. And we'll start just by defining an x and ny. So I'm going to start with like 13 points, ny 13 points. Lx is 1.0, ly is 1.0, dx is lx over nx minus 1. Can you guys see? Okay, maybe this, okay. And then dy is ly over ny minus 1. So that gives us all of these guys. Then we're going to define the u wall or u top, which is equal to, let's start with 1.0 top wall velocity, meters per second. Okay? So the first thing we want to do is initialize our domain. We need initial conditions for psi and omega. Where do we start? Start with zeros. Okay? So I'm going to do psi. So you type psi and press tab. It turns it into a Greek character. So psi 0 is np dot zeros. What is the size of psi 0? It's an x. Yeah. So we're not going to do. Okay. So that's a good point. Or do we need ghost cells? Why not? Yes. So that's what's so great about the finite difference with boundary conditions, is that you have a degree of freedom at the boundary that you can set directly. So you really don't need ghost cells, okay, in general. Right? So all we need to do is do nx and y for psi, and then omega 0 is np dot zeros, also nx and y. Okay? Now, on the initial condition, so remember, okay, let me get the slides back again, that psi was constant on the entire boundary, okay? So we said that psi is constant on the entire boundary. That constant can be anything. I'm just going to choose it to be 0. And our initial condition, therefore, for psi is already taking care of that. But omega doesn't have the boundary conditions yet. The initial condition on omega doesn't have the boundary conditions implemented. So we're going to go and correct omega 0 at each of those boundaries. Okay? And the recipe, so apply boundary conditions on omega 0. So we'll start with the, let's say, top wall. Okay? So for the top wall, actually, let's start with this. So we start with the left wall. Okay? So left wall. So what is the left wall saying? It's saying that omega 0 for all j is this stuff. Okay? So then omega 0 for all j, okay, at I equals 0. Remember, we index j and ji. That's going to be equal minus 2 times. Now, what is psi wall? It's 0. I'm going to assume it is 0. Okay? Or we can say, psi wall 0 if you want to be thorough. Psi wall minus psi 1j. So that's the psi interior. Okay? So you can either think in interior or indexing. So psi wall minus psi interior. So what is psi interior? That's going to be psi 0 on the first interior. So this is all j and 1. Correct? Clear? Right? Is this correct? So that's the interior point. If I equals 0 is at the boundary, I equal 1 is the first interior point. But across all of y. So all of j. Okay? And then we don't have a u wall on the left, so that term is 0. Okay? Now, if you want to play around with the split-driven cavity, you want to add, if you want to drag the left wall, then you have to add that term. Okay? Okay, great. So now we should be able to do the remaining walls. So that's left wall, and then right wall. So on the right wall, we can have the same formula, except for rather than I equals 0, -1, yes. And then rather than I equal 1 for the interior, -2, right? That's the second interior point from the end. Okay? -1, yeah. So when you access, if you're not slicing, that is going to give you the last point. If you're slicing, it's going to be an open domain. Okay? So the last point is -1. The last of the interior point, second interior point from the end is -2. Okay? Great. Now for the top wall, actually the top wall is going to be similar to the right wall with the indices swapped. Right? So we're going to take j equal -1. Remember our indexing from our logical indexing, we start from 0, j at the bottom, 0, 1, 2, 3, all the way to the end. Okay? So the top wall, omega 0, if omega 0 starts indexing omega, so initial condition omega j equals 0, j equal 1, j equal 2 to the end, the last point is -1 in the j direction. Okay? So omega 0 j equal -1 for all of x is 2.2 times psi wall, and then we just simply invert this guy. Oh, yeah, we forgot 2 over delta x squared. Thank you. So over dx over dx. So this one should be, so for the left wall, it should be dx squared, and for the other wall, should be dy squared. Thank you, Tim. dx. OK, so top wall, C0 at the top wall. So once we figure these out, then we're going to reuse those in the loop once we compute, because they're going to be the same. Okay? So 2 times psi wall minus psi0 interior, so that's -2 for all of x, over dy over dy. But we still have to add a term for the top wall, which is -2 over delta y times u wall. Okay? So -2 times u top over dy. Agreed? And then bottom wall, you can copy this and simply change this guy to 0. So that's j equals 0 for all of x. Omega j equals 0 for all of x. Bottom wall is 2 psi wall minus psi0 at 1, right, over dy dy, and then this guy is 0. Agreed? So to clean things up, I like to move the comments. OK, perfect. Are we good? OK. Now I'm going to start to set the some parameters for the simulation. Simulation parameters. T equals 0.0 initial time and time counter, essentially. I'm not going to pick delta t. I'm going to pick delta t from the stability conditions. Okay? But for the stability conditions, we need to define the diffusion, kinematic viscosity nu. We're just going to set it at 0.05, I guess. Yep. And so then for delta t, it is going to be the minimum of the two conditions that we discussed a few lectures ago. So what is it? The advection diffusion equation. Stability, 2D advection diffusion equation. Did we discuss the stability? I remember we discussed the, yes, so these guys, okay? So this is what I want. I want to pick, since we fixed delta t, since we fixed delta x, I want to pick delta t such that these two conditions are satisfied. So I'm going to pick the minimum. So if delta t is less than delta x squared over 4 mu and delta t is less than 4 mu over u squared, I'm going to pick the smallest one of those, okay? So that's what I'm going to implement here. So again, that's going to just give you a guideline, okay? So min of, what is it, 0.25 dx squared over mu. So min 0.25 times dx times dx. This is assuming dx equal dy, okay? So, you know, we can relax the assumption here and make sure that nx equal ny, etc. Okay? So 0.25 dx squared over the diffusion coefficient, and the other one was 4 times some velocity squared, and I'll discuss this in a second, what we're going to pick for that. Sorry, so 4 times mu over u squared. So 4 times mu over u squared. So which velocity are we going to pick for our initial choice for delta t? Where do you think the largest velocity is going to occur? At the top, right? Because that's there's no mechanism inside the cavity to increase the speed of the flow. So let's pick that velocity as the most conservative, as the worst case velocity, okay? And so I'm going to put ut, okay? That's kind of a good approximation, okay? So if we do this, you type in, so print dt equal dt. So that's going to give you a delta t, okay? Delta t, okay? In seconds. But I also would like to print the Reynolds number for this cavity. So print Reynolds number. So what is the Reynolds number? Is rho vd over mu or vd over nu. V is a characteristic velocity, d is a characteristic dimension. Since this driven cavity is driven at the top, so I'm going to pick that top wall dimension as the characteristic dimension, multiplied by the top velocity over nu. So that's going to be u top times Lx over mu. So for these conditions, our Reynolds number is 20. It's pretty nice and low. Okay. Now other parameters for the simulation. Let's do t end. I want to end this time at, let's say, t end is, you can choose a number of seconds or just 1,000 time steps. Okay, 1,000 delta t. Okay. Now we need to initialize a few other things for the solution. So C solution is an empty list, and C sol dot append is C0, right? Because we're going to animate things. And also for omega is a list, omega sol, and omega sol dot append omega 0. Omega 0. Okay, so we initialized our solution list with these guys. Okay, great. All on board? Okay. Now we're going to start our loop while, I always like to start loops like this, while t less than t end, t plus equal dt. Okay? So that's the first thing I'd like to do. Okay. So now, if you remember our algorithm, we said that our algorithm is going to consist of the following steps. And we should probably list it in these slides. So let's create a new slide, and I'll show you how the amazing art of creating slides in Keynote. Okay. Why is this not full? Right. Okay. So I'm just going to make this. Whoops. algorithm, maybe even solve for vorticity from, okay, solve for vorticity using existing, solve for stream function, sorry, stream function using existing vorticity, solve the vorticity transport equation, okay, and then so we solve the vorticity, repeat. Okay, pretty simple. But the first step was to solve for the stream function using the vorticity. And what do we do? Here, this is a Poisson equation. Poisson equation. Okay, so if you remember, we said we were going to use this iteration scheme for the Poisson solver. When delta x equal delta y, it simplifies things, but since some of your projects for this guy, we're not going to be assuming equal delta x and delta y, so you should be using this full formula. Okay, and we said this is the successive over relaxation method, so beta is typically larger than 1, but you can set it to 1 or less than 1, you get under relaxation. But anyway, so this is the solution, given a value for the vorticity and an iterate k for psi, okay? So the first order of business is to write this solver, okay? So that's what we're going to do. I'm going to embed the solver. You can write it as a function, but I'm going to embed it inside the for loop, because I always like to start as simple as possible. Okay? The more function calls you add, you may mess things up. You may be passing by reference or passing by copy, whereas you need a reference. So don't do that. Even if your code is going to look ugly initially, can start small and then make incremental steps and double check. An incremental step to clean up your code and double check, okay? All right, so let's do this. So what do we need here? We're going to need an iteration counter and a value for beta. So obviously, we need to monitor the error here. So the difference between k plus 1 and k for psi, the norm of that needs to be less than a tolerance. And also, I don't want to go over more than a maximum number of iterations. So I have a condition on my iterations. Okay, so while error less than tolerance and iteration is less than maximum iteration. That's what we want. So let's go ahead and set this in the simulation parameters. So beta is going to be equal to 1.5, let's say. And tolerance is 1e to the minus 3. You can tighten this tolerance as much as you like, okay? But I don't see a reason for doing that. Otherwise, we're going to be stuck just looping, looping in the loop, and then a maximum iteration. Max iteration is, let's say, 30 iteration stops. Okay. So for here, I'm going to start by solving the Poisson. So Mr. Poisson equation for the stream function. Okay. And I'm going to start setting my iteration counter equal to 0, and an initial error equal to 1e to the 5. That's my initial error, and that's the error we're going to drive to 0. Okay. So while error is greater than tolerance, so as long as our error is greater than the tolerance, and as long as our iteration counter is less than max iteration, do your thing. Okay, do something. Okay, so how do you suggest we do this? Obviously, first thing, for the right-hand side of this equation, of this solver, we need omega n. Right, so we need this omega n for sure. So let's go ahead and just grab that omega n. We're going to need it here. Omega n is omega sol minus 1. So that's the most recent value of omega. And it is going to be in the last entry of the omega sol list. Okay? Give you a minute to catch up. And please participate, kind of how, how are we gonna do this? Because I also forget. If I'm doing this on the spot, I'm gonna be I'm gonna need some help. Okay. Okay. Now we also need something for psi, right? Because obviously pk is gonna start from somewhere. So why not start it from the most recent value of psi? Okay, for the most recent value of psi. Okay, so then that tells me that I can get a psi n over here, or really psi is psi minus 1 dot copy. Now, why did I copy this rather than just grab psi_n? Because we're really not using psi_n. We're going to solve this on the spot. We're going to use psi and update it, use psi and update it. So I'm going to grab a copy of the old value of psi and work through that. Because if you think about it, the new value of psi at time n plus 1 is going to be equal to the old value of psi plus something. So let's start from there, from the old value of psi, but make a copy of it, and I'm just going to update it on the spot. Okay? And then I'm going to create an iteration counter psi k is equal mp.zeros like psi. So that's another copy for the iteration. And what's going to happen now, as I iterate, I'm going to take the difference between this psi and the iteration. Okay? Okay. So psi k is np.zeros like psi, but I'm going to initialize psi k only on the interior. Why? Because I need the boundaries of psi k to be 0. That's our psi wall. That's our constant. Okay? That was our constant for psi. Agreed? So only in the interior of a psi k, there's probably an easier algorithm, an easier way of doing this, but no, because a slice is not going to give you the last point, right? So it's a slice. Okay, so that is going to be equal to the interior values of psi_n, if you want. Okay. So that's psi_k. I froze psi_k. So I froze the iteration counter, and then I'm going to go through everything, update psi, and then take the difference between a new iteration and an old iteration. Remember, this is the iteration loop, and in here we're going to go over each and every point in the domain. So we're going to have a doubly nested loop now. We're going to go over all points I and j. Okay? So I always, we can start with j, we can start with I, whichever you like. For I in range 1 to nx minus 1, and for j in range 1 to ny minus 1. So what is range? What does range do? Try it. For I in range 1 to 10, print I. It's going to give you the first point all the way to the last point open, minus 1. Okay? So if you think about it here, I'm only looping over interior points. Why? Loop over interior points. I need to only loop on the interior points because I don't want to touch the boundaries. And secondly, how does this loop work? The first interior point in the Python indexing is 1. Okay, so the Python indexing goes from 0. We have nx points, so we go from 0 to nx minus 1. The interior points are going to be 1 to nx minus 2. And this is what this range does. Okay? Clear? So this is going to make sure you're covering only the interior points. Okay? And then we simply build this right-hand side. Okay, so there is a beta over delta 2, pardon me, dx squared plus dy squared. I'm going to keep that. I'm going to do that in the end. But first, I'm going to do like delta x squared, delta y squared, omega n, and then all of these kind of nice guys over here. Okay? So let's do this. Right-hand side. This is just a temporary. This is a scalar value. Okay? So we start dx times dy squared times omega n ji. That's what's so nice about the for loop. But make sure you index in ji, okay? So this is the first term, dx squared dy squared omega, plus dy squared. So what do we have here? Psi plus 1 plus psi minus 1. Now, although in my formula I have iteration index, we don't need that in practice. All we have to do is use psi rather than psk and psk plus 1, because psi is always going to have the most recent value. So whether you have a most recent value and an old value, it doesn't matter. Just use the value from the array called psi. Okay? So delta y, I plus 1 and I minus 1. So, yes, dx dy, thanks. Plus dy squared times, okay, so we said psi plus 1 plus psi minus 1, right? So this is going to be psi ji plus 1 plus psi ji minus 1. And then we have a similar term for j plus 1 and j minus 1, correct? We have a j plus 1 and then a j minus 1. Okay? So that covers all the terms that will be multiplied by beta over 2 delta x squared plus delta y squared. So what I'm going to do next is say RHS times equal, so that's saying take the right-hand side and then multiply it by beta over 2 over dx squared plus dy squared. And then finally, we say psij is the right-hand side, this whole thing that we just computed, plus 1 minus beta psij. Okay? So the cji is equal to right-hand side plus 1 minus beta times the cji. Okay? Now that, so this covers one iteration. This whole loop covers a single iteration. Okay? So now we calculate the error, and that's going to be a norm, lin algebra dot norm. We're going to do an L2 norm, and we're going to take the difference between psi minus psk. Okay? Now you can roll these out into flat arrays or not. It's going to still compute an error norm. And relatively, that's just going to be the same. Okay? So psi minus psk, is this correct? Yes, because now psi is actually psk plus 1. And psk is a copy of the psi, right? So perfect. And then update the iteration counter, plus equal 1. And once you're done, psi sol dot append psi. Oops. Psi. Okay. Do you want a minute to absorb this? So, good? Actually, what I'm going to do here is ravel, then ravel. Okay, so Python is weird when it's computing. Let me give you an example. So in norm, we understand the norm of a vector, which is like a measure of the length of the vector, for example, right? So, just like you have a Pythagorean norm, a squared plus b squared, that's the length square root of that. That's the length of a vector. We can do that for an arbitrary sized vector. If you have n elements in a vector, you just take the square root of the entire sum, okay? But what psi minus psk is, it's really a matrix. So what is the norm of the matrix? I really don't know what Python is doing there. So what I do with the ravel, I take for us, that matrix is really just points on a grid, okay? So I'm going to take all those points and lay them out flat next to each other. So that's what ravel does. It takes, so just do it as an example. A is mp.array, let's say 1, 2, 3, and then 4, 5, 6, okay? And then a.ravel is just going to give you a single array, a vector version. Yes? Here? No, that's psi. Yeah. You're updating on the spot. That's psi plus 1. Really, psi is psi plus 1, essentially. Yeah. Okay? Okay. So now we're done with psi. Work on omega. So we'll start by declaring an omega. And that's going to be, I'm going to make a copy of omega n. Okay? And now we can start assembling the different terms. Diffusion in x, convection in x, convection in y, diffusion in x, y, and then just combine everything together. Okay? So if you remember what we had here. So this is diffusion in advection in x, advection in y. Okay? And then, so actually we have a deep C dy, so this should be, we have a negative diffusion, a negative advection here, negative sign, right? So that term is negative, negative. Okay, so we have negative, so let's implement this. So this is psi plus 1 minus psi minus 1 over 2 delta y times omega I plus 1 minus omega I minus 1 over 2 delta x. Okay. So x convection term, Cx for convection, is minus, okay, psi. So what do we want now? We said psi, this is deep C by dy. So psi plus 1 minus psi. Okay, so if you're confused, forget about the j indexing. This is going to go over all x, okay? And we're going to do the interiors, okay? So first, look at the I indexing. And then what is j plus 1 minus j minus 1? So it's going to go from 2 to the end and from the beginning to minus 2, okay? Why did I start from 2? Because I don't want to include the interior points, the boundary points. So if you think about it, where are we evaluating the deep C by dy? We have to start, the first point where you evaluate deep C by dy is point 1. So that means psi I plus 1 is going to be at point 2. So that's why we start the subset from 2. Okay? That Cx is going to give us the convective terms on the interior points only. Okay? Because we don't need it at the boundary. We know the boundary values. Okay? So now it's going to get much faster. Over 2 dy times the omega version is going to be d omega by dx. So we have to just invert these guys. So we go over all j, and from I plus 1 minus omega, also all j, all the way to minus 2 from the end, over 2.0 over dx. Y convection term is similar. There's no negative sign. But now you have deep C dx. So you swap these guys. Or really what you can do, you can just type omega here. Okay? Because now this is omega, d omega by dy, right? So that's omega j plus 1 minus omega j, right? Over times psi. Okay? Pretty quick, huh? Once you figure it out for one term, it's just easy to do the rest. Okay? Now, diffusion in x. That is going to be d2 omega by dx squared. Okay? So we will do omega. So this really should be omega n, right? Because omega is zeros. That's going to be the new value. So dx is omega I plus 1 minus 2 omega I plus omega I minus 1. So we can just do this, omega I plus 1 minus 2.0 times omega n. Man, time flies really fast. 1 to minus 1, 1 to minus 1, minus 2 omega ij plus omega n, 1 to minus 1, all the way to minus 2. So you understand why I'm going from 2 here, right? Because the evaluating the convective terms and the diffusion terms on the first point in the interior. So I plus 1 is going to start from 2, not 1. So that we do 2 minus 0 is going to give us the value at point 1. Okay? There's no pens here anymore. There's no markers. And I don't have one on me. Okay? We did this with the advection diffusion equation. So, okay, so this is the diffusion term on in x, and then diffusion in y. It's going to be the same thing with the indices inverted. There's probably a way to invert things in Python. Don't do that, because you're going to lose clarity of what you're doing. Okay? So now finally, the right-hand side for the vorticity transport equation is Cx plus Cy plus mu times dx plus dy. Correct? So that's the right-hand side. Convection x, convection, yes? Yes, by delta x squared and delta y squared, sorry. Because I had copied from the one above. Thank you, Elizabeth. Okay. Right-hand side, convection x, convection y, diffusion x, diffusion y. And finally, we update our omega, but only on the interior, because the size of these arrays, really, based on all of these slicing here, these are interior points. So we're going to only update omega on the interior, and then apply boundary conditions. So then, omega on the interior, and the interior is 1 to minus 1, 1 to minus 1, always, is equal to omega n, the old omega. Remember, we're doing forward Euler, plus delta t times right-hand side. Does CFD get any simpler? This is CFD, still considered CFD. We're almost there. Okay? So now we apply the boundary conditions. Apply boundary conditions on vorticity. And boy, that's already ready for us. Where is it? It's right here. And you can just slap this in there and just change this. This becomes omega, right? That's essentially omega n plus 1. And this becomes C, the most recent value for the stream function. And then omega sol dot append omega. This is it. This is it. Okay. I'm going to walk around see if you have any concerns. Elizabeth is always skeptical of my work. Hopefully, well, actually, always with merit, right? Because she always spots my mistakes. Are you able to follow? Is this useful because you don't have the laptop with you? Yeah. He wants you to use Python? Oh. Okay, but it's still kind of useful. Yeah. Okay. Sorry, you have to use Fortran. It's pretty fast. It is very fast. For the naive, for the basic developer like us, it's pretty fast. It can deliver. You write the same code without doing anything in Fortran, write it in C. Fortran is going to beat C flat out. But if you tune your code on C, which is very complex, you can match Fortran. But it is such a complex, and I wrote a lot of Fortran in my life. In my project for undergraduate CS, I wrote an arbitrary precision calculator to calculate the square root of 2 to an arbitrary number of digits. So essentially, I define multiplications, divisions, etc., as operations on strings. So you can have an arbitrary precision, but man, it has an ugly syntax. Okay. Aaron, are you just copying?
I'm catching up.
Okay.
I understood what you said. I just can't
Okay.
type as fast as you were.
Okay. Do you guys want to try to run it? Just run it, and then plot something, see what happens. / for division. It's kind of pretty hard to see from way back, actually. I thought you had eye problems, but I can increase this a little bit. It's better. Okay. Let's try to get there in 5 minutes, and then we'll run this together. Okay. Did anyone run it? Okay, what did you get? Nice. Okay, that's with the Reynolds number 20. This is wrong. Yeah, we have. Let's see. Let me run the code. You have a mistake. Yeah, the streamlines should kind of be parallel to the streamline on the top. Okay. Let's see. I'm gonna run it with these things, and then maybe I have the mistake, Elizabeth. So, okay. Do you guys are you still copying from here? Okay. So I'm gonna try to run it and compare notes with Elizabeth. Sorry, actually have an error here. This is csol. Okay. PIP.contour f csol minus 1. Okay. So that's so Elizabeth results had the stream function kind of perpendicular to the wall. They should be parallel to this guy, okay, to the because there's flow between these lines, between these two streamlines, okay? So they cannot be emanating from the wall. So something with the boundary conditions, very likely, okay? Did you guys run it? Not yet? Okay, what, are you stuck? Oh, you just type it up. Work. Come on, Cx is minus deep C dy. Yeah, there you go. Okay, let's see.
Oh,
Did
that
you-
was even my vorticity, my stream function. It's not doing anything, it appears. So.
Oh, let's scroll up a little bit. Okay. Yes, thank you. Okay, so to see, it is in algebra while. So let's print your. Okay, so it is running. So there is something going on for sure. Okay. So let's print how many iterations this is doing. So at the end, so outside, yeah. So yep. Print iterate. 0 iterations. So you're not iterating. There's something wrong in the iterative solver. So while error and iteration less. Yes. You got that right. Error ck. No. Yes. This is right. This is right. Did you add e to the 5? Your error, you got to start with a very large error, right? Yeah. Okay. Yeah. It's a little bit better. Ah, there you go. Oh, sorry, Jebin. Did you get it?
No, I have some issue.
Oh, go on the CHPC website.
Yeah, I'll do that.
So were you not able to follow with us?
No, I can follow, but
I'm sorry.
I Python, so I have a problem there.
So yeah, worry about that later. Just yeah, work. Yeah, okay. What's up? So apply boundary conditions. You have something on the, what is it? What is the error? Name W is not defined. You used omega W. No, you use WN, but you don't have a new W. You have to define W is WN dot cop. Yeah, zeros like WN. Yeah. Aaron? Okay. Okay. Loop type built-in function. Okay, so let's scroll up. You probably are missing a multiplication or a division. Where is the error coming from?
The error says it's a built-in function method. It's not so straightforward. It's like telling CK is something that might exist in the system. I just tried changing it to PS.
And it worked?
No, and
It didn't work. Do you mind? CK K1 to minus 1 equals C. Oh, dot copy. Okay, so when you did dot copy, it thought, so copy is a function. So you need, oops, you need parentheses here. I don't know what I clicked. Okay. If you did not put the parentheses, Python is going to think it's a function. Okay, so try now. Very good. Okay, so now you have another int object. So you're missing a multiplication here. Typically, you have something in front of a parentheses 2. So dy squared times, right? So it's thinking 2 of, right? And same thing over there, dx squared. Yeah. Okay. Operands cannot be broadcast together. Okay, so this is for cy. So let's see cy. Yeah. Oh, comma, you have it, yeah, 2, and then comma, 1 to minus 1. 1 to minus 1. Minus 1. Yeah. Okay. All right. Hung? You got it? Yeah, good, good, good. Okay, and then I'm going to show you some fun stuff now. Okay, this is wrong. Vorticity? This is omega. Okay, show the stream function. Let's see the stream function. Okay, so if something is off with Aaron's code, but you're making progress. Did you get it?
No, wrong.
For psi?
Yeah.
Yes, so scroll up.
Fine.
Okay, so we need to debug this.
I have problems with
So it's very likely coming from your iterative solver. Okay. This is make sure you are iterating in the. So this is great. We're seeing bugs. Tim. Okay, so you're diverging. Your code is diverging over here. Okay, so when you see this, you're getting nans. Okay, so the first thing you want to double check is see if you are iterating in the iterative solver. That's the first thing, the easiest thing you can do. Go in the iterative solver and print the iteration count at the end. Make sure you are actually doing some iterations. Show me the initial error. Yeah, okay. Okay. Okay, so you are iterating. Okay. C-sol is still, so you still have an incorrect solution. So let's look at the boundary conditions. Make sure your boundary conditions are, okay, so they look like, let me show you my boundary condition. Tim, I'll come and check in with you in a second. Let's see. So, are you iterating? Yeah, yeah, print here, yeah, okay. Yeah, yeah. Print it, yep, print it. So go back up again because you have to reset the t end. It's already t is already greater than t end. So just run it again. Run from from this point, or actually run from the beginning, because you need to reset your arrays, your lists, your solution arrays. Okay. You need to reset your solution arrays. So make sure you start from the beginning. Oh wow, that's really high. Okay, Tim, I'll sit with you in a second because we're so close with. Okay. Okay, so let's see. So dx dy squared omega and then c dy squared and dx. So this is correct. Then omega and psi sol dot copy and then pck p dot ck is equal to c. So this is okay. Over here, it shouldn't. So the first time step, how much did it iterate? Let's see. So initially it iterated. So no, I wanted to iterate it outside.
Oh, okay.
So at the end, how many iterations? So it's each time. Okay. Yeah, it looks like it. You're right because. Yep. Okay. So at least the first iteration, the first time step, and then psipsol p dot 0 is like 2 dy, 2 dx. So let's see, nx, nx, lx, ly. Top wall, your initial vorticity, c minus 2, minus 2 ut over dy. Okay, so this is cj minus 1. T equals 0, nu, this is dt, 1000 dt, so dt is correct. T plus equal dt, so let's do, let's do, just want to do like 2 time steps, okay, and then we're going to try to debug it. Tn is like 2 dt. Yep. Then let's kind of, sometimes I like to restart everything. Okay. Okay. So to me, this is telling me that something is off with the boundary conditions, really. And then seawall, did you set it to 0? Yes. So, okay, there's your mistake. This is your mistake. Okay. Right here as well. Yep. I know why, because I started by assuming seawall is 0, and then I carried the negative sign. So then we can do cell, run all. Oh, what? Still wrong. Oh, omega, not omega 0. You're not updating your boundary, your solution.
Oh,
Okay. Okay, so now, fingers crossed, gonna do 1000 delta t's. Still a problem. Okay. C0, not C0. The most recent C.
Okay, because you're not.
Yep.
This is, you already set the boundary conditions. This is applying the boundary conditions
On their most
to
recent.
the new
Yes,
arrays that
yes,
you're
yes,
making.
yes. But still, it's doing 30 iterations. Don't know why. Okay, I'm gonna. Okay, so we still have an issue, I think. Mx, C2, C0, omega 0. This is still running. Okay, kernel interrupt. Kernel interrupt. Interrupting, still stuck in the iterative loop. Oh crap. Kernel shut down. Okay, I'm gonna close. So yeah, control file save. Yeah, I always do command and save. Okay, so I'm gonna close it. And then which one? You need to use anti-aliasing for your fonts. This will be better for your eyes.
Okay.
So there's an option in the settings for fonts.
Yeah.
Do anti-aliasing. Your fonts are all kind of aliased. They're kind of, they will cause eye strain. Okay, so I'm gonna do a few time steps instead of tolerance e to the minus 3. I'm just gonna do 2 delta t's. Okay, this is still problematic. Omega 0. Let's see. Yeah, you still have issues? Oh no, you can. Elizabeth is our ambassador to the CFD. So double check these guys. Let's see. Omega n, and then omega n, omega n. And so yeah. So dx is I plus 1. So I plus I minus 1. dx. plus delta t. So your iteration, I'm going to scroll up, look at, so let's look at this. Mokbel, are you still stuck? Okay, you too attract bugs. Okay, so we start iteration 0, adder, omega n is omega solution, psi is psi sol, -1. Did you add psi sol in the beginning? Yes, psi sol, psi 0.
There it is.
Okay, that should fix it. Scroll up, up,
Up.
up. Okay, scroll down a little bit, go down. Okay, so you have C0 and omega 0. C wall, omega 0, C0. And okay, so okay, this is okay. Okay. Omega m is omega c sol minus 100, copy. Ck is mp dot 0 is like psi. Then cji. Make sure you got this right. Dy squared, then I plus 1 plus I minus 1, and j plus 1 plus. So how many iterations are you doing? 30? So print the iterations outside at the end of the while loop, right? Because we want to know just the last. Yeah. So and do like 2 time steps only. Just do 2. So 2 delta t end is 2 delta t, and then run from the beginning. So your arrays are initialized with the right. You make sure your arrays are initialized, right? Okay. Okay. So run it now. Let's see. You're doing 10, 10. What's your maximum iteration count? 30. No, so you're doing maximum iterations. So you still have a bug. You shouldn't do max iterations. Okay. So do 30. Put 30. But you should get. So something is off with the initial condition. Pretty sure, yeah. So let's see. Where's initial condition? C1 minus C0. So make sure that's correct. I'm going to scroll back up to the initial condition. Hang, is yours working? Okay. So look at the initial condition. Did you set psi wall correctly? Omega 0. Yes. There you go. That's your bug. So rather than dragging underscores around, just put it omega 0. Why the underscore, right? So it would be faster for you to type. Yeah. Rather than dragging an underscore around. Okay, there you go. Now, yep. Yeah. So plot the solution. There you go. Okay. All right, Tim. Did we get it? No? No. Okay, is your how many iterations are you doing?
I know for sure that's what's breaking it.
So how many you should get
One iteration, which means it's not doing anything. Like it's
you
zero
in here. So your initial, start with your initial condition then. Let's go back to your initial condition and make sure your initial condition is correct. So you have C0 on the left wall and then C0 on the right wall. Are these correct? So column 1, column -2, -2, and then 1. dy minus 2 ut. Okay, are you reinitializing your arrays when you try it again? Hold on. Okay, so you have it all in one cell. That's good. Okay. And you're saying it's just doing one iteration? So put TF equal 3 delta T. Okay, 3. Yep, and run it again, please. I want to just run it.
I've been,
Oh, trying to break.
yeah, so that just does one iteration.
Okay, so you're doing
Now I'm
1, but then you're doing 30.
Oh, I
So,
see.
okay, so you have a problem then in the update. So you're using the correct C. Then your right-hand side plus V. What is V? That's new. That's your diffusion term, right? Okay.
Negative.
Negative, yep. So there you go.
Yeah. I think I changed that.
No, no, no,
Oh,
no.
oh.
Minus CX plus CY, right? Because there's a minus deep C dy. Jeben, did you get it? Okay, so you still have a problem.
Oh, I guess is it just?
No, no,
Oh,
no, that's wrong.
Okay.
That's wrong. That's wrong. Still wrong. You shouldn't be doing 30 iterations this early. Wow, speaking of debugging, huh? Okay, so now you want to look individually. So this is deep C dy times d omega dx, and then deep C, so d omega dy times deep C dx. Okay, and then RU sol append psi, and then psi is c sol minus 1 dot copy ck. Okay. So just for kind of every time when you're using kind of numbers and multiplications, make sure you put 1.0 and 2.0, just because Python sometimes is going to treat certain numbers, certain multiplications as integers. No, iteration is an integer, right? But for like when you're doing over 2 delta x, make sure you put it like over 2.0, because sometimes, I don't think this is the case here, but sometimes, yeah, minus 2, so omega n dy. So I think your diffusion terms are okay, but I think now you have a problem with the boundaries. Yeah, but you have the signs correct. Over delta x squared, right? So we have the boundary conditions correct. Psi wall. Okay. So I think we're out of time really, but I'm gonna post my code, but I want to show you how cool this is. Okay. So for my results, like you get this. I want to show you a little couple of things that you really need to do, and I'm gonna copy those just because they're not essential. But like one of the first things you want to double check is that you are actually divergence free. So is div u equal to 0? And that's something that you need to check. But I want to show you kind of a nice, interesting figure that I typically do with these plots. Okay, so psi sol. Okay. Okay. So this is what a high quality lid-driven cavity looks like. But let me take the Reynolds number. Now, as you increase the Reynolds number, you're not only increasing the speed here, essentially. So you increase the Reynolds number either by lowering the viscosity of the fluid, so air rather than water, for example, or increasing the speed here. What's going to happen, you're going to move this what's called primary vortex a little bit kind of further to the right. But the effect of that is that you're going to start seeing secondary, tertiary, and more vortices be created at these corners. Okay? And that's something you're going to explore in one of your projects. So I'm going to put more grid points here, maybe 33. Okay? And I'm going to make my Reynolds number a bit higher, maybe. Let's see. This is going to give me a Reynolds number of 200. Okay? 200. And I'm going to run 1,000 time steps. Still running. And you can do an animation and all of these fun things, but I really want to continue on this. We need to make sure that div u is 0, because that's the condition for incompressibility. Okay? So once you compute the velocities, you need to calculate a div u. The velocities are easy to compute, so they're the derivatives of the stream function, and then you do another derivative on the velocities. Okay, so this is done. Let's see what happens at a Reynolds number of 200. Look at that. Okay, it's not steady state yet. Okay, it is not steady state yet, but it's moved this primary vortex over here, and you have a recirculation zone over here. Now, what you're seeing here is really not a steady state solution yet. So these are not really streamlines over here in the back. But this is the primary vortex. You're moving it to the right. Okay, you're dragging all the fluid to the right. So what would you expect for the pressure in this case? If you remember our discussion on the meaning of the pressure and dilatation. So you're pushing fluid here. What is the pressure going to do? It's going to resist. So you're going to have very high pressure here, very low pressure there, right? But anyway, one of the projects is to look at what happens if you double the size in the x direction or double the size in the y direction. You change the aspect ratio. How many vortices like this are you going to develop? And as you change the Reynolds number, these secondary vortices over here, they're going to become much stronger. Okay, and they will have an impact on, let's say, if you have heat transfer involved in this problem, which is going to be one of your projects as well. So we're going to have 3 projects. I'm just typing them up. We'll discuss those on Thursday. But I think I'm going to, you either create your pairings or I'm going to pair you together. And it looks like, you know, in light of today's exercise, I don't know how you guys want to pair. Do you have a preferred team member you want to pair with? You don't care? So maybe Elizabeth and Tim, okay, and Hong and Jebin and Mokbil and Aaron. No? Is that fair, or is that reasonable? Okay. If not, we can change. I mean, I'm just kind of trying to, and that will make your life more easier. But I'm gonna try to type up the projects. There's gonna be 3 projects. You can pick whichever one you like. I hope you pick different ones. You don't all pick the same one. But they're gonna be, the first one is gonna be looking at the driven cavity with different aspect ratios and different Reynolds numbers. But you're gonna have to go and dig in the literature, see what others have done on all the projects. There's not a single answer. You're gonna have to come, stand up, and give us a presentation about your findings and write a small paper on this. The second problem is gonna be taking the unit aspect ratio driven cavity and adding buoyancy and heat transfer to the problem. So this wall is gonna be heated, and there's gonna be some buoyant effects for the fluid here, but also this wall is gonna be bringing in fluid at a cooler temperature. So this will be, let's say, 300 K, and this will be 600. So, and then the question is gonna be, look at the temperature distribution for different Reynolds numbers, okay? Or what is the controlling parameter in this case? Is it the Schmidt number? So, you know, looking at viscosity versus diffusion coefficient for heat transfer. But you're gonna have to add a term to the Navier-Stokes equations and rederive a new vorticity transport equation. And the third one is really open-ended. I haven't seen anyone do it before. It's to simulate the flow in a rocket motor. So you take a channel, inject on the sidewall, and just do the flow, okay? So I have an analytical solution for that. And the challenge there is figuring out the boundary conditions. So you have a wall at the left, and you have injecting boundaries, top and bottom, and you have an outflow on the right.